In our study of infinite series to date, we have looked at determining the convergence of series with positive terms, and most recently with series that alternate in sign, alternating series. But what about determining the convergence of just a general series, one that doesn't necessarily have positive terms or terms that alternate in sign? We want to work our way towards being able to determine the convergence of those. So the first concept we're going to introduce here on our way to that is this. We say that a series converges absolutely if the series consisting of the absolute value of the terms converges. So here's what we mean by that. The question is to show that this series converges absolutely. Now this series on its own, if you take a look at it, is an alternating series, and we could actually show that this series on its own converges by the alternating series test. But we want to show that it converges absolutely. So what that means is we're going to take the absolute value of the terms, which is what I'm doing there, and basically what's making the terms negative, of course, is this negative 1 to the exponent. So if we absolute value, it reduces to this. And so really this question is asking us, does this series, the series in which all the terms have been made positive, does it converge? And of course the answer to that is yes, because we've talked about this series before. This is a converging p-series with p equal to 2. So since the series of positive terms converges, we therefore say that our original series converges absolutely. Not only did the original series converge, but the absolute value of the terms, that series, converged. And that brings us to this very important theorem, which says that if you can show that the series of positive terms converges, that will mean that the original series converges. And this is a powerful theorem because the series that we're talking about here is a series of any type. It doesn't necessarily have to be a series of positive terms, alternating terms. It can be a series of some positives, some negatives. And what we're saying is that if we can show that the series of positive terms converges, then we will know that this original series, it converges as well. In other words, what we're saying is that showing absolute convergence will imply that our original series converges. Now, as great as that theorem is, you need to be careful with it, because what the theorem does not say is that absolute divergence, that does not equate to the original series diverging. Here's an example of that. So let's consider this series. It's an alternating series, and in fact it's the alternating harmonic series. And we've previously shown that this alternating harmonic series converges by the alternating series test. However, if we take the absolute value of the terms, so I'm taking the absolute value of the kth term, which is reducing to this because the negative 1 to the exponent is the positive and negative part. This series here, the absolute value of the terms is the harmonic series, which we know diverges. So the absolute value of the series diverges, but the original series converged. And when this kind of thing happens, we call this a series converging conditionally. So just to read through it, if an original series, and this again is of any type, positive terms, alternating terms, or some positives, some negatives, if a original series converges, but the absolute value of its terms diverges, we say that the original series converges conditionally. So in the case of our alternating harmonic series, we say that the alternating harmonic series converges conditionally. So let's work our way through a couple of examples here. To classify each series as converging absolutely, converging conditionally, or being divergent. So we have our original series, and if I think about k being 1, k being 2, k being 3, I can see that I have a series here in which the terms do not have a consistent pattern between positives and negatives. Sine of 1 radian, sine of 2 radians, sine of 3 radians, depending on what radians we're at, will determine the positive or negative value of sine. So to determine the convergence of a series that's not necessarily positive or alternating, we can first of all check for absolute convergence. Because remember, absolute convergence will tell us that the original series converges. So we're going to check for that first. By the way, remember with any series you want to check the nth term test quickly just to make sure that it has a chance of converging. If we took the limit as k went to infinity, our kth term would go to 0. So that part's good. The nth term test equaling 0 holds. But now let's check absolute convergence. So I now have a series of positive terms, and I can use any of the tests that I've studied in the past, comparison, limit comparison, integral, ratio test, to test the convergence of this series. What I'm going to do is I'm going to compare this series with 1 over k cubed. I know 1 over k cubed will be bigger than or equal to sine of k over k cubed absolute. I know that because sine k is going to oscillate between 0 and 1. And this is 1. So I know that this will be less than or equal to the terms of this series for all k. Now the reason I'm doing that is I'm setting myself up here to use the comparison test. I know that this series is a converging p series, p greater than 1. And I know from the comparison test that if the larger series converges, then the smaller one will. So writing that argument up, we're saying that since the absolute value of my original series is less than or equal to 1 over k cubed for all k, and since I know that this series is a converging p series, therefore by the comparison test, my smaller series must converge. And since I've shown that this series converges absolutely, when I say this, it means that the original series converges absolutely. I therefore know that my original series converges. Here's another example. This is actually an example of an alternating series, so I could check the convergence of this series by the alternating series test. But what I'm going to do is I'm going to check for absolute convergence first, because remember, if it's absolutely convergent, then the original series is convergent. Again, if I check the nth term test, if I take the limit as k goes to infinity, I can see that the terms will go to 0, so this series has a chance of converging. So let's begin by checking absolute convergence, which is the absolute value of the original series, which is equivalent to this. I don't need the bars now because with k that represents positive terms as it is. So I want to check the convergence of this. Now actually I don't have a very good feeling if this converges because I can kind of see here that I don't think the 1's important and k squared over k cubed is going to be 1 over k. If I were to compare this series to this one, which I know is the harmonic series which diverges, I have a feeling that's going to mean that my series here diverges. Alright, let's check this out. This time I'm going to use the limit comparison test. And I'm going to do the limit k goes to infinity of the series I I want to test compared with the one I know. And so that reduces to and as k goes to infinity, I can see that that's going to go to 1. And remember, with the limit comparison test, if I get a finite value, it means that if the series that I know that I've used diverges, then the one that I'm testing does the same. In this case, it diverges. So putting my argument together nicely, since this series is the harmonic series, which I know diverges, and I've used the limit comparison test, testing the limit of the series I'm finding out about compared with the one I know, and I'm getting a finite value, something greater than 0. Therefore, by the limit comparison test, I know that the absolute value of my original series, it diverges. In other words, the series diverges absolutely. Now we need to be careful, because just because my series diverges absolutely doesn't mean that my original series diverges, or converges for that matter. We need another test to determine that. So we need to go back to our original series and test it. So it turns out we actually will need to use the alternating series test on this series, since that's the only way we know how to test a series of this type. And the first thing I need to do with the alternating series test is show that the k plus first term is less than the kth term for all k, and we're talking about the positive part of the term when we do this. So k plus 1 squared over k plus 1 cubed plus 1, is that less than this? I think this is true, but I'm not completely certain. So what I'm going to do in this case is I'm going to take the derivative of my series. I'm going to think of it as a function, and I'm going to just see if the derivative is always negative, because that will tell me that my terms are decreasing. So I've worked the derivative out here in advance. The derivative is this. And if k is positive, the denominators of the derivative is positive. On the top, if k is 1, I would get a positive number there. But if k was 2 or more, I would get a negative on the top. So what I'm saying is that this derivative is negative if k is greater than or equal to 2. And so the terms are decreasing from term 2 onward. So they are decreasing eventually. That's all I need to show. And so I know that this condition is met. The second part of the alternating series test I need to check is if the limit of the terms goes to 0. And that I can see is true. And so the two conditions of the alternating series test hold. Therefore, my original series converges. So putting this argument together nicely, I've shown that the terms are decreasing for k greater than 2, and I've shown the limit of the kth term approaches 0. Therefore, I know that the original series converges by the alternating series test. And so to answer the question, we say that this series converges conditionally because this series itself converges, but the series of absolute terms, absolute value, diverges. And so this series converges conditionally.